What specific problem does the proposed method aim to solve?
The proposed method aims to solve the problem of the local reasoning barrier in transformer-based models. Specifically, the method focuses on understanding and overcoming the challenges faced by transformers in efficiently learning tasks that require global reasoning and complex compositions of information. The method introduces the concept of distribution locality as a measure to determine when weak learning is achievable by transformers. It also explores the use of scratchpads, particularly educated and inductive scratchpads, to break the locality barrier and improve the learning capabilities of transformers on tasks such as syllogism composition, cycle tasks, parities, and additions. The goal is to enhance the model's ability to generalize and learn efficiently on tasks that involve complex reasoning and composition of information by leveraging scratchpad methodologies and addressing the limitations posed by the local reasoning barrier.
How does the proposed method work? Illustrate step by step.
The proposed method works by introducing the notion of distribution locality, which quantifies when weak learning is efficiently achievable by transformers. The distribution locality measures the minimum number of tokens required, in addition to the token histogram, to correlate non-trivially with the target. This measure applies to any data distribution on tokens without needing to infer a distribution class from model invariances. The method then provides results based on the distribution locality, including a general conjecture claiming efficient weak learning is achievable by a regular transformer if and only if the distribution locality is constant. Additionally, a theorem is presented that proves the negative side of the conjecture in the instance of a variant of the cycle task under certain technical assumptions. The paper then explores the use of scratchpads to help with the locality barrier, distinguishing between agnostic scratchpads and educated scratchpads. Agnostic scratchpads are extended to cases where a polynomial-size scratchpad is used by the transformer without supervision, showing that efficient weak learning is still not possible if the locality is non-constant. Educated scratchpads are introduced to break the locality of a task with subtasks of lower locality, allowing transformers to efficiently learn tasks that may originally have high locality. The concept of inductive scratchpads is then presented, which exploit induction to break the locality barrier and improve out-of-distribution generalization. The inductive scratchpad is implemented by using special tokens to separate the question from the intermediate states and by promoting induction through attention masking and reindexing positions. This method is shown to improve OOD generalization on tasks like the cycle task, parity functions, and addition tasks by breaking down the learning into easier sub-targets with lower locality.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method described in the paper include the ability to quantify the notion of locality, or local reasoning, barrier, through the concept of distribution locality. This measure provides a tight proxy for understanding efficient weak learning of regular transformers for arbitrary data distributions. Additionally, the paper introduces the notion of inductive scratchpads, which can break the local reasoning barrier with appropriate mid-steps, leading to improved learning outcomes. The inductive scratchpad allows for the promotion of inductive behavior in tasks that require iterative operations on state variables, such as graph algorithms, optimization algorithms, and arithmetic tasks. Practically, the method of using scratchpads, particularly educated scratchpads and inductive scratchpads, can enhance learning by breaking down complex tasks into easier subtasks with lower locality. This approach can improve out-of-distribution generalization and length generalization on tasks like parities, additions, and the cycle task. By designing scratchpads that facilitate step-by-step computation of the target function, models can efficiently learn and generalize on tasks that may have high locality barriers. The inductive scratchpad, in particular, allows models to learn more reasoning steps than seen during training, leading to better OOD generalization and improved performance on tasks requiring iterative operations.
How is the method validated or tested?
The method is validated or tested by introducing the notion of distribution locality, which quantifies when weak learning is efficiently achievable by transformers. The distribution locality measures the least number of tokens required to correlate non-trivially with the target, without requiring an orbit argument to infer a class of distributions. The paper provides a general conjecture backed by experimental results that claim efficient weak learning is achievable by a regular transformer if and only if the distribution locality is constant. Additionally, a theorem is presented that proves the negative side of the conjecture in the instance of a variant of the cycle task under certain technical assumptions. Furthermore, the paper explores the use of scratchpads to help with the locality barrier, introducing agnostic scratchpads and educated scratchpads. Experimental results are provided to show how educated scratchpads with constant autoregressive locality allow transformers to efficiently learn tasks that may originally have high locality. The concept of inductive scratchpads is also introduced to address the sensitivity of fully educated scratchpads to the number of reasoning steps, leading to poor out-of-distribution generalization. The inductive scratchpad is implemented for various tasks such as the cycle task, parity functions, and addition tasks, demonstrating improved length generalization and OOD generalization. The results and experimental findings are detailed in the paper, showcasing the effectiveness of the proposed methodologies in overcoming the local reasoning barrier and enhancing learning capabilities of transformers.
What results were achieved with this new method?
The new method of using inductive scratchpads in the paper achieved significant results in improving the out-of-distribution, OOD generalization, and length generalization for various tasks. Specifically, for the cycle task, the inductive scratchpad allowed the model to generalize to more reasoning steps than seen during training, enabling better OOD generalization as the distance between nodes increased. For the parity task, the inductive scratchpad facilitated learning parity functions efficiently, with the model able to generalize to up to 50 to 55 bits from training on up to 30 bits. Additionally, for the addition task, the inductive scratchpad enabled length generalization from 10 to 20 digits and even up to 26 digits using different methods, showcasing the effectiveness of the approach in improving model performance on tasks with increased complexity and length requirements.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method presented in the paper include the sensitivity to the number of reasoning steps when using fully educated scratchpads, leading to poor out-of-distribution OOD generalization. This can result in overfitting on-in distribution samples, as seen in the cycle task example where the model quickly achieves perfect accuracy on the training distribution but fails to generalize OOD due to overfitting the scratchpad length. Additionally, the method may not fully utilize the fact that each state is generated from the last state by applying the same operations, potentially limiting the ability to increase the number of induction steps beyond what was seen during training. Furthermore, the inductive scratchpad approach, while addressing some of these issues, may still require careful design and implementation to ensure effective learning and generalization, especially in tasks with complex dependencies or longer sequences. Overall, while the method shows promise in improving learning efficiency and generalization in reasoning tasks, there are challenges related to designing scratchpads, managing the number of reasoning steps, and ensuring effective utilization of intermediate targets for inductive learning.
What future work do the authors suggest?
The authors suggest exploring future work in several directions based on their findings. Firstly, they propose investigating the use of scratchpads in learning tasks to enhance learning capabilities, especially in tasks requiring global reasoning. They also recommend further research into the concept of inductive scratchpads, which have shown promise in breaking the local reasoning barrier and improving out-of-distribution generalization. Additionally, the authors suggest exploring the application of inductive scratchpads in various reasoning tasks, such as graph algorithms, optimization algorithms, and arithmetic tasks, to further understand their effectiveness in promoting induction and improving learning outcomes. Furthermore, they propose studying the impact of attention masking and re-indexing positions in implementing inductive scratchpads to facilitate proper induction and enhance learning efficiency. Lastly, the authors recommend investigating the potential of inductive scratchpads in achieving length generalization in tasks like parities and additions, as demonstrated in their experiments.